Hello, welcome to another session. A student requested that I post this derivation for Kepler's third law. So if you remember, Kepler's third law is about a planetary motion, which is elliptical, and from this distance is same as your axis, and this is equal to 2a, and this is the cm of the planet sun system, and the planet is replaced by a particle mu, and mass of the sun is capital M, and mu is almost the mass of the planet, and we follow the motion of mu. And okay, so a lot of things that in the previous videos you may want to consult that. We've derived quite a bit of things. So for instance, we've derived that if the eccentricity of this thing is epsilon, and this is the position from the center of mass, and this is the direction is theta, and this is x-axis, and this is y-axis, and this is an xy plane, then r is given by some constant r0 over 1 minus epsilon cosine theta. So r is any time t, and theta is time t. So this is and there are r0 and epsilon related to angular momentum, and that was given as follows. So r0 is L square over mu times alpha. Alpha equals to g mm. So that's one relationship. And epsilon is another relationship. So I looked up, and epsilon is this. Okay, so how do I get this from these considerations? We look at angular momentum conservation. Okay, so in this situation, we have let's look at this. L is L equals to mu at some point r square d theta dt. We look at like that, and we say, okay, let's put dt on the other side and mu on the other side. So L over mu dt, these are all constants, and the other side becomes r times r d theta. So if you look at in this d theta, so that this is the area swept out. If this is d theta, then this is the dA. So this whole thing will be this is r, and this side is r d theta. This is like a triangle. So this is equal to 2 times the area of the triangle that swept out the area. And if you go all the way around once, you'll be area of the ellipse. So if I integrate this all the around once, 0 to 1 period, this will be the area. So this will be L over mu period will be 2 times the area, which will be pi times AB. This is the area of the entire ellipse. Now this has the information, this leads to that. Okay, and in particular it gives me it gives me k, explicit expression of k, if the constant of proportionality there. Okay. So to complete that, we need expressions of a and b. So b is in terms of this r0, b is r0 or square root of 1 minus epsilon square, and a is r0 over 1 minus epsilon square. So this was you can show it from here. You can try to say x minus c square over a square plus y square or b square equals to 1. You can convert this equation by knowing x equal to r cosine theta and y equals to r sine theta. If you put this in here and you carry out the calculation, you can figure out a has to be what b has to be, what c has to be. And c is the distance to the center, and b is that distance. That's what b is. Now, you can see that I can write b equals just square root of 1 minus epsilon square times a. Then I can write everything in terms of a. And so this like 2 times pi times is square root of 1 minus epsilon square a square. And then we can convert this like t. T is equal to 2 pi square root 1 minus epsilon square a square. Then there's a mu, and then there is L. Now L goes from here. We can use L. Let me erase some of this just so I get a more space to write on. I didn't erase it. I think I can pull it off over here. Change the pen color. So from this, I want to get L. I have L square is equal to mu alpha r0, and if I square it, let's square this thing, and then we have a whole square. So we have a t square equals to 4 pi square 1 minus epsilon square a to the power 4 mu square, and L square is mu, and then we have alpha. Alpha is given by that mu times alpha and r0. Okay, this is inverse. This is equals to a at the denominator, this together, and so this a will cancel one of this and make us cube, and this mu will cancel one of the mu's, and so we have 4 pi square mu over alpha a cube. So this is the k, which can be written as 4 pi square mu over g m m. Now the mu is this, so you can see mu will cancel this thing, and only this will be left in the denominator. So this will cancel this thing and just make it m plus m in the denominator. So the k is just going to be 4 pi square for g m plus m. Kepler thought k did not depend on the planet, but you can see in this here K depends on the planet. So unlike Kepler, K, so the K depends on planet. But pretty mildly, is the mass of the sun and this is the mass of the planet. So through this sum, mass of sun plus mass of planet, and to the extent that mass of planet is really very small compared to the mass of sun, you can kind of simplify it. If you simplify it, this gives this is the Kepler's result, that T square is proportional to A cube, and the constant proportionality is almost independent of the mass of the planet. Okay, this is pretty interesting that Kepler's laws can be so readily derived from just angular momentum conservation aspect of Newton's derivation. Well, we will use this in some problem settings pretty soon. So see you in another video. Bye.